So, good morning, everyone. Thank you very much for inviting me today. I want to thank my colleagues. It's great to be back in Poland. So, my name is Julian. I'm a tech evangelist for AWS. I'm based in the Paris office every now and then, because most of the time I am traveling and meeting all of you guys wherever you are. And again, it's a pleasure to be here. Today, my topic is deep learning for developers. And Rafal just told me it's kind of a weird title because until very recently, deep learning was something that maybe only 100 people in the world could really do at expert level. And actually, that's the only purpose of my talk today. It's really to show you that, and we're not connected. And really my purpose today, I guess that's going to be better in a second, is to show you that if you're a developer, you can do this, right? You can actually get started with deep learning. If you can code, you can do deep learning. And of course, you won't be able to do as much as the expert do, and my colleague Shri this afternoon will probably make your head spin much more than I will. But you can get pretty far, and I'm going to show you today how to integrate deep learning in your applications without being an expert. So I'm going to start with a crash course on deep learning, and there's a bit of theory involved, so take a deep breath, have coffee, and bear with me for 20 minutes. I really need to introduce a few concepts, and I promise you these are really the minimum concepts you need to understand the code demos that I will do later on. Okay, so don't feel uncomfortable if you miss some of the details. You can always look them up later. My slides, of course, will be available, and all of my code will be available. Just try to understand, the basic concepts. Okay. All right, so let's get started. So first of all, just a quick recap on where we stand on AI. This is our current AI stack, and of course we keep working on building new services and new blocks for that stack. So watch this space. At the lowest level, we have infrastructure. You can use CPU instances, GPU instances, and now even FPGA instances to either build or train or use your deep learning models. Okay, and we have a wide family of instances that you can grab. And as a reminder, starting Monday, they will be built per second, right? So some cost savings there probably. On top of the infrastructure layer, we have those deep learning libraries. We provide an AMI, an Amazon Machine Image, which is called the Deep Learning AMI. You'll find it on the AWS Marketplace. That comes pre-installed with all those libraries. Okay, and at this level, of course, you need to be a developer. You need to know what you're doing. But again, I'm going to show you how to do this with MXNet today. And you can build, train, optimize, use deep learning models and then later on integrate them in your apps. On top of this, we have a managed service layer that will basically simplify infrastructure management for you. We have Amazon Machine Learning that lets you build and use prediction models very easily, zero infrastructure to manage. We have Amazon EMR, which is our managed Hadoop ecosystem where you can run MapReduce jobs, Spark jobs, etc. Again, with very little work when it comes to infrastructure, and we have more services that are also, typically involved in building machine learning applications or pipelines like Kinesis, Batch, or ECS if you want to run for example, your training or your prediction jobs in Docker containers. And then at the very top, we have high-level services. One for chatbots, voice or text, called Amazon Lex, which uses the same technology as Alexa. And you heard about Alexa quite a lot this morning. We have another service called Polly. It should be called Polish, right? Because it's really built here. So, how about a round of applause for the Polish engineers who build this stuff? Come on. Great job. Great job, guys. And And so you can do text-to-speech in 24 languages. And we have a third service called Rekognition, which does image detection, image classification, face detection, face comparison. And those three ones are really just API-driven, no deep learning required. You just use APIs and get the job done, right? And usually it's a one single API call. So you know, there's a little bit for everyone here. And again, we'll keep expanding that. But today I'm going to focus on this lower layer, right? How do you code deep learning models, okay? And I'm going to do this with a library called MXNet. So, okay, now is the time for that deep breath and that extra caffeine. Let's look at neural networks and again, the minimum you need to understand to be comfortable with this. So, here's a neuron. Hi, neuron. So what's a neuron? A neuron is basically it's a construct that takes a number of inputs, right? So these are going to be numbers. They could be pixel values. They could be word counts. They could be anything, right? So the x's here are just the different inputs. Each input is going to be multiplied by weight, right? And as you can see, as we'll see in a few minutes, weights are really the cornerstone of deep learning and training. So we're going to multiply each input by weight, and then we're going to sum everything, right? This is called the multiply and accumulate function. You'll see that in research papers, right? Multiply and accumulate. So that's what we do here in the bottom left corner, okay? So we take those two vectors, and we just use the dot product to get the result, okay? And so that gives us that U number, that output. And that's going to be a numerical value, okay? And that's fine, but that's not enough. We want to run that value through a function, which is called the activation function. Here on the right are some examples straight out from Wikipedia. And please go to that page and read all of it if you can't sleep tonight. And the purpose of the activation function is to introduce non-linearity, right? So here comes the jargon again. So in simple words, what this means is sometimes we want the neuron to be activated, right, to actually output something that is significant because, you know, the inputs were significant for what we're trying to achieve. And sometimes we want the neuron to not output anything, right? And that depends on the use case, and that depends on the application, and this is why we have multiple activation functions. So this, as you can see, all these functions here, some of these functions are really nonlinear, like the rectified linear unit, which is quite popular these days. And as you can see for this one, if the output value from the multiply and accumulate operation is negative, then the output of the neuron is going to be 0. If the output of the MAC operation is positive, then the output of the neuron will be that exact same value. So we force the neuron to say, well, given the inputs, right, I think I should have an output or not, right? And that's kind of a way, you know, if you think about brain neurons, sometimes your neurons will fire and let electricity discharge, and sometimes they won't, right? And that's exactly the same thing here. That activation function is used just for that. Sometimes we want the neuron to fire, and sometimes we don't, okay? And we use the activation function for this. So if you put all those neurons together, you start to build layers, okay? So we'll have an input layer, okay, with our X values. We'll have an output layer with our Y values, and the Y values will be the predicted result. So imagine we're trying to classify images, right? We would input pixel values as X's, and we would have a number of possible categories for that image on the Y layer. And so in each of the Y neurons, we would have the probability that the image is of this given class. Okay, let's say we have 100 classes. We would have 100 output neurons. Each of them would store the probability that the image belonged to class Y, class I or class J or whatever the numbers or the names are. Okay? So this is a simple neural network, right? Input layer, output layer, and in the middle, hidden layers. So here we have just one. And as you can see, they're fully connected. Okay, so each input neuron is connected to all the hidden layer neurons, and all the hidden layer neurons are connected to all of the output neurons. Okay, fully connected network. And we have a single hidden layer here, but as we'll see in a minute, we can have multiple layers to increase network complexity and accuracy, hopefully. So if we want to run data through the network, we need to build our data set. And in all the examples out there, you will see it's usually called X again. Okay, so I will have M samples. Okay, so each line is a sample. Okay, and each sample has L features. Okay, and for the the output layer, we need to have that Y matrix, which contains the exact value that we're expecting for each sample. So if my network works correctly, when I use that X11, X12, etc., when I use that first sample here, okay, so take this, rotate it in your head, put it on the input layer, right? Okay, run it through the network, and then you would read the output layer, and you would expect that this category, so it would be, let's say this is category 5, for example, right? Number 5. So you would expect the highest probability here on neuron number 5 on the output layer, right? Okay? So this is really how we're going to build our data. So in the examples that we'll see in a few minutes, you will see the X matrix, the Y matrix, and the purpose, the whole thing that we're trying to do here is to adjust all the weights in the network automatically, so that once again, when I show this to the network, the output is correctly predicted, and when I show this one, I get this one, etc., etc. So on paper, it's quite simple, okay? And we'll measure the performance of the network by comparing the actual predictions, the correct predictions, with what we call ground truth, with the actual exact result that we're expecting. So if we have a well-trained network, it's actually, going to score pretty high. It's not going to miss a lot of predictions. Okay, so this is what we're trying to achieve. So in order to do this, we need to adjust the weights. Okay, and this is the training process. So the training process initially will start with random weights or initialized weights, but they will be pretty far from the final result. So not the best weights will be available initially, of course. So when we start running those samples into the network, we will get a lot of prediction errors, right? Initially, the network will do a poor job at predicting the correct output. Okay, and this is called prediction loss. Okay, and there are many ways to compute them using loss functions, and that's part of the architecture of the network too. So the purpose of training is to minimize loss. Okay, so we're trying to lower the loss as much as we can, and that should increase accuracy, right? If we reduce the prediction error, then the actual accuracy should go up. Okay, and that's the purpose of training. So again, we need a way to run the data set through the network again and again and again, and find a way to automatically adjust the weights in order to decrease loss and increase accuracy. Okay? And so the way to do this today, the accepted way, is an algorithm called backpropagation combined with an optimization algorithm. Okay? So backpropagation was invented by this gentleman. And it's an algorithm that, based on data samples that have been forwarded through the network, right? And based on the actual loss that has been measured compared to the ground truth, that algorithm will then go back. That's why it's called backpropagation. So it's going to go through the network, starting from the output layer up to the input layer. And it's going to adjust weights layer by layer in a way that it would reduce loss. Okay, so we have no time to go into the math details. Again, you can look it up. It's well explained in many blogs and pages and I guess on Wikipedia too. But that's the purpose of backpropagation. Okay, first we run some samples, we measure prediction loss, and then using backprop we go back the other way and adjust weights by tiny steps in a way that we know is going to reduce error. Okay, and how do we know that? We know that because we use an optimization algorithm. Okay, so the purpose of the optimization algorithm is to tell you which direction you should change weights in order to reduce loss. So let me take a simple example and then we can generalize it. Imagine you have a function like this, right? That uses two parameters, okay? And that if you graph it, it gives you something like this, okay? And you would like to find the x and y values that give you the smallest possible value of z, right? So in geometrical terms, it would mean actually finding the lowest, quote-unquote, point in that graph, okay? So this is exactly what we're trying to do, because in our neural networks, we have a function like this, right? We have the prediction loss, which is a function of all those weights, right? All those parameters, okay? The problem is, of course, we don't have only two. We have thousands, millions, tens of millions of parameters. So if you wanted to think about this in deep learning terms, you would have to think about, let's say, 50 million dimensions, right? Not 3. So I don't think none of us can do that, right? So let's stick to 3D. So we would start with random or, reasonable values of x and y, and that maybe would put us here. Okay, and we need to get there. So that's what the optimizer does. The optimizer is going to start from that high point there, and it's going to look what happens if, where basically should I increase x or decrease x, and should I increase y or should I decrease y? For each dimension, which direction should I go to get a lower value of z? Right? Make sense? Right? All right, no one's leaving, so that's, maybe you're paralyzed or maybe you're following me. Following me? Yeah, all right, you rock. Okay, so this is what SGD does. That's the most famous algorithm. There are more efficient ones now, but you will see SGD being used quite a lot. Still, it's probably the easier one to understand. So we're going to take small steps, right? We're going to take a step in the right, quote-unquote, directions, right? In the right x direction, in the right y direction to decrease z. And we're going to do that over again, and again, and again, and again, right? So we're going to walk step by step down the mountain and hopefully find the lowest point in the valley, okay? The step size is called the learning rate, okay? And it's one of the key parameters in building a successful training model, okay? So you could say, yeah, okay, so let's do that all over again until we really find the lowest point and then done, job done, right? Well, the problem is there is such a thing as learning too well. So theory says that if a network is large enough and if you give it enough time and data, it's going to learn it perfectly. And when I mean perfectly, I really mean 100%, right? So all the math majors out there can rejoice in the fact that, oh my God, it's perfect, right? 100% accuracy. The thing is, it's 100% accuracy on the training set, right? Now, what about the new samples? What about the real life samples? What about the samples that come from data that your users generate? Will they be 100% accurate too? In other words, will your network generalize well? Will it adapt well to data it has never seen? It depends, right? If you train it too well, then you're going to run into a problem called overfitting, which is a well-known machine learning problem. And that problem is you learned the data set, the training data set so well that actually it's too perfect and you cannot successfully predict new samples. Again, going back to a 2D thing, I'm guessing you're all familiar with logistic regressions. You have a x and y, and you put some dots, and you try to find a straight line that fits best, quote unquote, again, those points. Well, okay, it's an easy thing to do, right? But what you want is really a line, right? If imagine you overfit and you actually have a curve like this that hits perfectly every single point. You could say, wow, that's 100% accurate. And now if you throw new data samples, you will have poor results, right? Because that curve that you found, it's too specific, right? And the straight line is actually a better model, okay? That's the exact same concept here. Okay, so we're trying to find a model that is good enough on training and good enough on validation. So we need to know where to stop when it comes to training, and so the training data set obviously is not enough. We need extra data to measure how well the model does on data that hasn't been used for training. So if you've done machine learning before, this will be familiar. We're taking the data set, we split it in three. The larger chunk will be used for training. A smaller chunk will be used for validation. So validation means running samples that haven't been used for training into the model to see if we're overfitting or if we're correctly generalizing. Okay, again, these are not used for training, just to measure accuracy. And typically we'll keep a test data set that we just use at the very end on the trained model to benchmark this model against models that you've been building over the weeks and months and years, right? So this is just to have a reference point on the actual performance on the finished model. So training means this. It means taking the training data set, running it through the network. And we're not going to do this sample by sample. It would be too slow, so we actually batch them. Okay? So we take maybe 32 samples, run them through the network, measure loss, run back propagation, adjust weights, try to walk a little bit down the mountain, and then we push the next batch and we do it all over again. And we do the full data set like this, batch by batch. And when we get to the end of the data set, we have run what we call an epoch, and we start again, right? So we train for multiple epochs, maybe 100, maybe 200 epochs. So we're going to run the full data set batch by batch through the model 200 times, right? Now you understand why we need GPUs. And then, so the key parameters here again are number of epochs, batch size, and learning rate, right? How fast do you go down the mountain? How many samples do you run at a time through the network to measure loss and optimize? And how many times will you run the full data set through the network? Okay. And when you're done with this, you have a trained network. Okay? And these are called, the hyperparameters. Now, validation, like we said, is important because it's going to tell us when to stop training. Okay? So we're going to take that smaller data set, and after each epoch, we're going to run those samples through the partially trained network, measure loss, and measure accuracy specifically, and see if the network is learning properly, right? So that validation accuracy should go up. But if it starts to go down at some point, it means we're overfitting, right? And training accuracy could still go up because we're adapting too well to those training samples. But actually on other samples, we see accuracy going down. And this is when we should stop training, okay? So this is why you need to monitor those two accuracies during training. We'll see them. And of course, you need to save the weights after each epoch in order to potentially go back to an earlier epoch, which is the one that generalized best, okay? And MXNet will do all of this easily for you, okay? So far I just talked about fully connected networks, and they're still widely useful. But there are other architectures, and I just want to touch on those for a few minutes and before going into the demo. So I'm sure you've heard of convolutional neural networks. It's quite a mouthful, CNN. And well, I'm sure people will contradict me, but my sources, I should ask Alexa. But my sources tell me they've been invented by a French guy, right? So I need to mention that. So Yann Lequin, who's one of the top AI researchers right now, and is running the Facebook AI lab in Paris as well. And in the late 90s, he came up with that convolution architecture, which is extremely good at classifying images and extracting features from images. And that was really a major breakthrough for AI, being able to successfully perform image classification and image processing with neural networks. And those led to the first industrial applications for banks, for example. Banks use this to read, handwriting and for a check processing, right? You still remember checks, right? Yeah, all right. I can see a few older people here, all right, like me. Okay, so CNNs, really, really, really good for images, and we're going to prove that in a minute. And the last one I want to mention is and now we're getting into weird territory. It's called LSTM. And that's really a weird name. So how could something be long and short at the same time? Always strikes me as not really obvious. So they're called long because they have many layers, and short-term memory because unlike the network architectures I just mentioned, these neurons keep a state of previous computation, right? If you think about the fully connected network, it's a machine, right? You feed stuff, it computes, it forgets, it doesn't store anything, it just runs the computation, and then you do that all over again, right? With LSTM architectures, you can have memory. You can remember earlier computations. Okay, I won't go into the details because that would be a 4-hour session right there. Okay, so an LSTM neuron can compute its output based on the input, of course, and also a previous state. Okay, so in other words, they have memory. And so that makes them really good at predicting sequences, right? If any of you wants to predict the Bitcoin prices for the future, that's probably what you want to use, right? Good luck with that. For me, I'll stick to machine translation. I'll show you an example of using LSTM to translate German into English, right? And these are really sequences, okay? Because words are, sentences are a sequence of words, and sometimes it's very likely that word A is going to follow word B with a high probability, right? So, in a nutshell, that's the theory. Okay, so now you can breathe. We're going to go into code. But again, this is the crash course on deep learning. And again, don't worry if some of it sounds weird. You can go and read again. There are lots of good resources out there. But in my opinion, right, this is the minimum you need to know and understand to do training successfully, right? So yeah, you need to invest a little bit of time to understand those. So let's talk about MXNet now. So MXNet is an open source library. It's part of the Apache project, so it's really independent. We have contributors from the industry and from academia. I think last time I checked, the top committer to MXNet was an Apple employee. I think AWS has 4 of the top 10 contributors. We hired some people who actively developed that previously. Lots of researchers are also contributing. So it's really a joint effort, and we're really happy to see the project join Apache. So AWS is using MXNet as its preferred library for a number of reasons. First, it has a larger language support than other libraries. You can do Python, C++, R, Scala, Julia, and I'm probably forgetting a few more. So that's good, because our customers use a lot of different languages, so it's important for us to also support tools that are widely available. The second thing is MXNet scales really well, as I will show you in a minute. It's important for training if you have very large jobs. MXNet is also quite memory efficient compared to other libraries, which means you can actually run MXNet models on small devices, less powerful devices, or devices which are constrained, which are memory constrained, like my little Pi here. And these are really the main reasons, right? Wide language support, scalability, and memory efficiency. And of course, a high-level API that is easier to use compared to other libraries. That will allow you to build all those different network architectures that I mentioned, fully connected, convolution, LSTM, and more. Okay, so, and I'm going to use Python. Again, you could use other languages. And with this, in just a few lines of code, you will be able to define your model, train it, save it, reuse it, etc. And you can build all those different use cases that you see here. Image processing, video processing, text, etc. Pretty much anything, right? So just a word on scalability. We run that benchmark on scaling training from 1 to 256 GPUs. So that's quite a lot of GPUs. And the red curve is linear scaling. And as you can see for some of the more complex models, we scale pretty linearly. So that means if you train, let's say, ResNet with a 256 GPUs, it's going to be almost 256 times faster, maybe a little less, than training on a single GPU, right? So that matters a lot because when you train on huge data sets, when you train on pictures, can you imagine the training sets for Alexa? Can you imagine the training sets for Poly and recognition? It's huge, right? So if you run that on a single GPU, it's never going to complete before the sun explodes. So we want to actually deliver something to you guys a little sooner. And of course, we need to run on a lot of GPUs to get results and get updated models fast enough. Okay? So that's really interesting. So the question is, how do you get to 256 GPUs? We don't have a single server that can support that. The largest we have in AWS has 16 GPUs. It's called the P216X large, and you can start one in a few minutes. So we can easily do distributed training with MXNet. Okay, so we're able to use, in this case, for example, 16 servers with 16 GPUs, and share the data set across the instances, and train and speed up, right? And that's quite easy to do. Okay, enough slides. Let's jump into the demos. So I'm going to show you 4 things. I'm going to show you how to use a pre-trained model, right? Which is great because less work, so it has to be great. Smarter people have built and trained models, so we can just grab them and use them. Then we're going to do image classification from scratch, okay, on a smaller data set. Then I'll show you machine translation with Sockeye, which is an open source project coming out from AWS. And finally, we'll play with the robot. All right? So let's get started. Okay, so here we go. So basically what I'd like to do here, I'd like to take a picture. Yeah, this one. Right? Oh, no. Sorry. Let's copy my screen. Yeah, that's better. So here's the picture. I want to know what's in it, right? Simple question. So here, I'm going to, so I wrote, no, that's not the one. I wrote a simple Python program using the MXNet API, and that's 65 lines, so anyone can do it. Okay, and here what I'm doing is, as you can see, let's look at the bottom layer, the lines first. I'm loading 3 different models, pre-trained, right? So I downloaded them from the web. Actually, MXNet has a web page called the Model Zoo, where you can grab pre-trained models. So I just download them. I load them in memory, and boy, is this complicated. It takes 1 line of code. Okay, that's all it does. And then I'm running my image through all 3 networks. Okay, and I'm going to find out about the categories. So all 3 networks have been trained on a data set called ImageNet, which has objects, which has been trained on objects and animals, and it has 1,000 different categories. Okay? So that's as simple as it gets. So actually most of the work, and that's not surprising, is to actually load the image, right? If you're doing data work, you know that 90% of the work is actually getting the data ready for processing, right? So unfortunately, it's still the same with deep learning. Maybe we could have a deep learning model that builds, that loads data automatically. That would be great, but not today. So I'm loading the image with OpenCV. I'm splitting the image into red, green, and blue channels, because this is what the model expects. It's been trained on blue, green, and red channels. Okay. I'm resizing the image to 224 by 224, which again is the size of image that the network expects. And I'm building the input shape that I'm going to feed into the network, right? And as you can see, so it's going to be one sample with 3 channels, each of them 224 by 224. Okay, so it's my input sample is a 3D sample. Okay, right? It's a 3D tensor. Okay, 3 by 224 by 224. All right. Okay, so that's just Python stuff. And actually, the interesting thing is this, right? So to predict, I take that 3D tensor, I push it through my network with that forward API. I'm reading the outputs. Okay, so I'm reading those 1,000 probabilities on the output layer. I run a little bit of Python craziness to sort the 1,000 probabilities and get the top 5. Okay. And yeah, either you love or hate Python, but for this kind of thing, it's really great. Okay. And then that's it. I print my top 5 probabilities. Okay. That's what I do here. So once again, 1 line of code to load the network, 1 line of code to run the sample through the network, and a few more lines of code to actually load the image and sort the probabilities, right? But the MXNet API here is really just a few lines. So should we do this? All right, so and as you can see, I'm running this on my Mac, right? So it's CPU based, not GPU based. So the first model tells me I have 46% probability of a stage, 24% probability of an electric guitar. I would say that's quite accurate. The second model tells me I've got 87% probability of a stage and 4% of an electric guitar. Well, that's quite good as well. And the third one tells me 45% of a stage and 43% for electric guitar. Okay? So we find the same categories because the models have been trained on the same data sets and the same categories. But as you can see, different models will give you different results, right? So that's an important learning. You may need to try different models to see which one works best for your kind of data. Okay? Simple enough, right? Okay, let's move on to the second example. So here I'm running on AWS. I'm running on a GPU instance. And this one has 16 GPUs, right? That's more than we need. So what we're going to do here is we're going to learn the MNIST dataset. I'm sure you've seen this before. It's like the Hello World dataset when you were doing deep learning. So it's 60,000 samples, 60,000 handwritten digits, okay? And the name of the game is we'll show you a digit, and we show the model a digit, and it should tell us if it's a 0, or 1, or 2, or a 9, okay? And again, here it's much simpler because those are really almost black and white images. So there are 28 pixels by 28 pixels. So I can take each sample, transform it into that matrix here with pixel values from 0 for white, for black, to 0 for white actually, and 255 for black. Okay, and this is what I'm going to run inside the network. Okay, so how do we do this? Let's try a simple model. We talked about the fully connected network. So let's build one, okay? And this is what we do here. And that's 8 lines of code or something. So we define the data layer, the input layer. We fully connect it to a hidden layer with 128 neurons. Again, we fully connect that layer to a second hidden layer of 64 neurons. And then we fully connect it to the output layer, which has how many neurons? 10, right? Why 10? Because we count from 0 to 9, and that's 10 categories, okay? So I'm going to load my data set here. I'm going to, why am I running this on the GPU? Oh yeah, I am running this on the GPU, yeah, fine, okay. I'm binding the model that I just created to the data set that I loaded, right? I set my optimizer to SGD, and then I train the model, right? And those iterator objects are going to take care of serving the data set batch by batch, right? Remember, we're running them batch by batch, so thank God we don't have to do this manually. Those iterator objects will do this, okay? And then I'm going to save my model, and I'm going to see how accurate that was using the validation data set. So let's run this guy. Huh, sorry. And that should be reasonably fast. Okay, so we're going to see the epochs going by. Okay, well, that's very fast. And you can see training accuracy going up, and we can see validation accuracy going up, right? And it takes half a second per epoch. That's very fast because it's a simple data set. So we run for 20 epochs, we save the model, and using the validation data set, we see that we have 95% accuracy. So is that good or is that bad? So let's check with real-life samples. So I did what I had to do. I took my paintbrush application. I drew some ugly digits. Wait till you see the 9. Yeah. Really ugly. And now let's take those images and run it through the train network, just like we did for my guitar player earlier. Okay, exact same code. Load the image, put it into that ND array object, that tensor, and then run it into the network. So we can predict. Just need to use the right one. So I'm loading my model, I'm loading my image, preparing it in that array, and again I'm forwarding the array into the model, and then I'm doing this for all 10 digits. Okay? Let's do this. Okay, so for each digit we get 10 probabilities, right? So we read a probability on each of the 10 output neurons. So how well or how bad did we do? So the 0 is 56% a 0, which is very disappointing, because I think it's a nice 0, right? How could you not be sure this is a 0, actually, right? Anyway, the 1 is okay, right? Which is reassuring. 2, not so great. 3 is actually nice. 4 is not great. 5 is not great. 6, 7, and 8 are bad. And as you can see, 9 is completely wrong, because it thinks my 9 is a 3. Okay, so I knew it was ugly, but not that ugly. So that's a bit disappointing, because again, based on validation accuracy, I should be hitting the result 95% of the time. Using my sample, I'm not. So I could train longer, I could do more work, but maybe I need a better network, right? And so I said earlier, convolutional networks are very good at images, so how about we build one? And actually, this is the exact one you saw on the slide. It's the Yann Lequin network, which is called LeNet. That's a great name. And as you can see, it's not very easy to build. It's not very difficult to build, sorry. So you could read the research paper, understand the MXNet API, And you could actually do this, right? And people are doing this, actually. They read the research papers, and they built that fantastic state-of-the-art model using the API. And sometimes the researchers are so nice that they will have done that already for you. And maybe they even have trained it, so you can, again, go to the model zoo and use it. But here's an alternative. Just define it yourself, okay? And that's not a lot of code. We're going to use 3 GPUs because we need a little more processing power, and the rest, why am I using Adagrad here? And the rest is the same, right? Optimizer, iterators, save the model, etc. Okay? By the way, please note how easy it is to use GPUs here, right? If anybody here has tried to do a CUDA programming, low-level programming, you know it's hard. Here, if you need GPUs for training, this is how you do it, right? The first line would train on CPU. This one would use a single GPU. This one would use all 3. So let's do this. It's not easy with one hand. All right, so let's see how much time that takes with the 3 GPUs. Go, GPUs. Okay, so it takes about 2.5 seconds per epoch. Okay, so that's 5 times longer than the previous model, but keep in mind we are running this on 3 GPUs, right? And each of them has thousands of cores. So you can see the computation, the computation requirements for CNNs. If you try to do this on your CPU, I think I tried it last night, and on my machine, and it was something like 45 seconds per epoch, right? So if you want to, again, that's a very small data set. Think about very large data set. You cannot complete this on CPUs. You need GPUs, right? So we see accuracy was pretty good very quickly, right? After a couple of epochs, we already have 90+% validation accuracy, and we get to 98.2%, right? We could get way beyond 99 if we train a little more, maybe. Okay, so I saved the network. How about we predict again, see what happens there? And of course, I need to change the model. And hopefully, I will get better results this time because, again, CNNs are very good at images. Okay, so this is much better, right? We have very high scores. Okay, 99, yeah, this one maybe not. This one's really a little low. And my 9 is still not great. So probably I need to train a little longer, right? I shouldn't have changed this parameter. It was better last night. Okay, so yeah, it's 20 epochs is maybe a little too low. But as you can see, generally the scores are much higher. And I could actually get to 99% on that ugly 9. Okay, so here's an example of selecting different network architectures, training, and looking at results. And of course, this is very fast because it's a small data set, but you can grab many different data sets out there and run longer trainings and do more complicated things. So before we jump to the robot, I want to show you really quickly Sockeye. So like I said, Sockeye is an AWS lab project. It's using LSTM networks, and it does machine translation, okay? So grab this thing from GitHub. There's a very cool blog post as well on the AWS AI blog, which I recommend. And there are a few tutorials in there, so you can get started, right? So AWS Labs Sockeye. So what I did is I grabbed a training set with German sentences, quite a few German sentences, right? And the same one translated in English, right? Okay, same ones. So how many do we have? So it's 1 sentence per line. Okay, that's a lot of lines. Okay, almost 6 million sentences, right? And so I run this thing for a number of hours. Took about 4 to 6 hours on 8 GPUs. And that LSTM network learned how to translate German into English. Okay? So let's run some examples. And so these are sentences that I grabbed from German news websites, right? These are not test samples that have been built to be perfect, okay? I literally grabbed those from the Der Spiegel and a few other places. So let's try all 5. I would say that's quite good. That's quite fast too.
If anybody speaks German, we encourage you to confirm or not.
Yeah, if you have German or Germans, maybe, yeah, just yell at me if that sounds weird, right? But the German comes from the newspaper, so it should be good German, right? Then the English speakers could actually complain about the rest. All right, so this one is especially for you guys, right? Okay, so it's a pretty good translation, I think. Let's do few more. This one, nice. Typical German sentence, right? 50 character words. Still, you know, it's not perfect English, but you can understand the meaning of the sentence, right? And maybe let's do the final one. Oh yeah, I want specially for you guys. Yeah, I should do that. How could I forget? Yeah, this is quite good, right? And that's the apostrophe over there. So it's not a bug. It's expected that we have that. And the last one. Yeah, it's quite good. It's quite good. I mean, it's there are no errors in this sentence. So you could say, yeah, maybe it's a little awkward, or maybe it's not exactly the meaning, but it's very, very close. Again, 4 or 5 hours of training on 8 GPUs using those samples that I showed you, right? A few million sentences, and the vocabulary is about 25,000 words. So it's more than we need. And here's Sokai, right? So if you need machine translation, you can just train, get the models, and put this in your app, right? Open source stuff. I think it's brilliant, right? And this was built by our team in Berlin. I have our development center in Berlin. So yeah, if you want to clap, just clap. Yeah! Thanks for them. Okay, and now let's do silly stuff, right? Alexa, what time is it?
The time is 2:13 p.m.
Okay. And I'm late, I guess, but I'll be done in a few minutes. Alexa, open Johnny Pie.
Johnny Pie is at your command. What would you like me to do?
Go forward.
Okay.
Move forward. Turn left.
Okay.
Go backward.
Okay.
Turn left.
Okay.
Stop.
Thank you for interacting with Johnny Pie. Goodbye.
Okay, so yeah, that's a combination. That's a combination of all this stuff, right? So I like to call this AI end-to-end because I'm using, as you can see, Alexa and the Echo devices from our Cambridge colleagues. So well done. This works really well.
I don't know that.
Yeah. somebody in your team is, you see? When I say great work, Dave, it says, no, I don't know that. So I'll let you handle that, right? Okay. So I wrote a skill, right? And you saw that from Max's presentation was very good as well. So I defined a skill interface with a few utterances and slots, etc. And I call a lambda function, which is indeed great to interact. And that lambda function pushes a message through AWS IoT. So we go back to the Dublin region to send a message. It comes back here because the robot is listening to that to those messages, and then it moves using the Raspberry Pi library, right? I should mention that the skill that I wrote is not public, right? So you cannot install it on your Echoes. Whenever you write skills, they stay completely private until you decide to publish them, and then someone at Amazon will validate them. Okay, so don't worry. You can actually test stuff locally. It never gets published without you pushing the publish button. Okay, so this works pretty nice. Now, let's do something more. Let's actually try to call that recognition service from the robot and see what happens there, right? It's harmless, right? It's a friendly robot. No, it doesn't have any weapons. Let's try the deep field thing. Alexa, open Johnny Pi.
Johnny Pi is at your command. What would you like him to do?
Do you see faces?
Okay.
Five faces have been detected.
Okay. That's Polly. Okay, so let's make sure we saw you. So how do I know? Come on. Oops, no, that one here. Yeah, it's got a Twitter account. Oh, wow. See? Recognition. Okay, well, phase 2 and 3 are pretty dark. We still see them, right? Because the lighting is really going my way. Okay, so here I'm calling recognition. Well, actually, the robot is taking a picture, calling recognition. Recognition does that face detection thing, sends back some JSON information, which I use to actually highlight the faces. And then, of course, it tweets and it speaks using the Great Poly service. Okay, one last thing. This is very cool, but I need a cloud connection for that image processing thing. And maybe I want to do local processing. Maybe I don't want to go to the cloud to do image detection, right? So let's take this guy here. And let's see what we can do here. Okay, so here I'm going to ask for a different thing. And the robot is going to take a picture and use a pre-trained MXNet model to find out what this object is, right? And this time it's strictly local, running on the Pi, using a pre-trained model like I showed you earlier. Alexa, open Johnny Pi.
Johnny Pi is at your command. What would you like him to do?
Do you see an object?
Okay.
I'm 11% sure that this is a piggy bank.
Fail! All right. Let's try and understand why. This is terrible. A piggy bank? No, that's not. Okay. Move closer. Come on. I'm ashamed of you. Alexa, open Johnny Pi.
Johnny Pi is at your command. What would you like him to do?
Do you see an object?
Okay.
Yeah. Get it right this time.
I'm 55% sure that this is a golf ball.
All right, close enough. Which is weird because, you know, when I did the same thing a few days ago, it was 99% sure it was a baseball. So anyway, all right, close enough, okay? And let's, you know, so some people think that robots are going to take over and destroy us, but I would say with these guys, you know, we're pretty safe right now, okay? But thank you anyway. And just as a side note, flying with all this stuff through customs is a lot of fun, right? I was trying to explain the other day that to a Ukrainian custom officer what this was all about with the limited English that they had, and I had a good time. Anyway, they let me through, and I'm thankful for that. Okay, I'm almost done. So thank you very much. You can find more resources here. So that's the MXNet website. Sockeye, which I mentioned, the Amazon AI blog, and all of the demos and all of the code that I showed you is available on GitHub. And I have a number of blog posts on Medium where, you know, I give way more detail on all of this, all the demos that I did and more. So please go there, learn, ask questions, and start to implement deep learning in your applications. Thank you very much. Thanks again for having me. And thank you for listening.